Hello, everyone, and welcome back to AE 311. This week, we're going to focus on photometry and the quantities that make up the units of lighting, and as well as the equations that underpin those quantities. We'll also take a look at measurement devices. For example, this monstrous goniophotometer right here. Don't worry, the more relevant tools that we'll be using in practicum are handheld ones, not room sized. So let's go ahead and jump into it. We'll start with a roadmap. So much like the vision and perception lecture, what we need to get our photometric quantities is basically just two things, and that is a light source and a visual system. First stop along our path today is going to be luminous flux. So luminous flux is a measure of the total light emitted in all directions by a light source. And the way that that light is emitted, the distribution of that light doesn't affect that quantity at all. It's just the total light emitted. Building on that, we can consider luminous intensity. So luminous intensity, unlike luminous flux, does care about where that light is emitted. And in fact, it's specifically the flux emitted in a particular direction. When flux emitted in a particular direction reaches a surface, we call that illuminance. And illuminance is just a measure of the total light striking a surface from all directions. Similarly, we can consider the light leaving that surface. We call that exitance. And exitance is a measure of the total light leaving a surface in all directions. And if we consider a particular direction, we're talking about luminance, which is the actual quantity of light that you see, that you experience. This is the measure of light actually entering your eye. And to round us out here, we need to include at least transmittance and reflectance, which are two of the ways light interacts with a surface. So here's our roadmap. Let's dig into that. Starting with luminous flux. This is, in just a couple words, photopically evaluated radiant flux. Okay, so we did touch on this last week in vision and perception, and the fundamental equation for this quantity is this. And so you see here a couple key pieces. First off, we have this equation below me, and you'll notice the V lambda. The V lambda is our photopic spectral sensitivity curve that we were discussing extensively, and this defines the quantity of light actually experienced by our visual system. Now, we multiply that by P lambda, and P lambda is the power emitted by a light source. So let me give an example of that. So there we have below me right here, we have a standard architectural LED. That's that blue pump YAG phosphor LED. And then we can evaluate the power of the spectrum of that LED across the visible range, which is 380 to 780 nanometers, using the V lambda function. And the V lambda function is what defines the lumen, or luminous flux. So that is the phi over here on the left side of the equation, hence our symbol of phi and our unit of lumen. And the last thing I want to mention in this equation is that value of 683. That's simply a scaling factor to bring the lumen in line with previous definitions of lighting power. So let's take a quick look at this equation what we have here in a practical sense, we're very rarely going to use that integral. In fact, we're going to turn that into a sum most of the time. And essentially, all we're doing is taking a table like the one you see here, and we take that table and evaluate the power in watts of the SPD of the light source, and then multiply it by the relative sensitivity of our visual system, or the V lambda function. So that's what that equation looks like. So we have lumens, or luminous flux, is equal to 683 times the sum of the power of the light source at each wavelength times the sensitivity of our visual system at each wavelength. So let's take a closer look and break this equation down. So we can see here, first off, we just need to take P lambda times V lambda, right? So the SPD times the V lambda function. So that gets us this set of values. Now, if we sum them, that'll get us to 5.72. But we need to multiply that value by our scaling factor of 683. So that will get us to our final value of 3907. So that's how we evaluate this function to get the lumens of a light source. Taking a look at how we measure luminous flux, we're going to use an integrating sphere. So an integrating sphere is a sphere. It can be enormous, like the one shown on the slide, but I actually have a compact one. So it really depends on how big your light source is, because the light source needs to be embedded inside it. Now, typically the inside of these things is going to be coated with this material called spectraline, which is this ultra white material. It's actually, interestingly, the same stuff we use on space shuttle heat shields, because it's so evenly reflective and universally reflective and absorbs almost no light. So you'll calibrate your integrating sphere with a standard light source, and then you're going to attach a spectroradiometer, which then measures it at a point. However, that point measurement can be relatively scaled as a ratio of the reference source, making these integrating spheres a very reliable way to measure the total light output of a light source. Now, you're not going to need to do this. Don't worry about it. I just wanted to give you some background as to where these values come from. You're going to get the value of lumens for any light source from the manufacturer's cut sheet. So that's just going to be provided because manufacturers are the ones that do this kind of measuring. Moving on to luminous intensity. So when we're talking about luminous intensity, we're talking about the luminous flux in a particular direction. We'll define this with the symbol I and the unit candela. And let's take a look at that equation real quick, because we need an additional value here. So it's not just luminous flux, but it's luminous flux over omega. Omega is actually the solid angle in steradians. So when we're talking about solid angle, we're talking about something like this. Solid angle is a three-dimensional angle. So imagine a cone defined by the central angle at the light source. And all light within that cone is going to be within that amount of steradians. And we're going to take a closer look at solid angles on Wednesday and really dig into spherical coordinate systems, because we do need to understand those to understand photometry well. But for now, we just need to know that the steradians of the solid angle is a particular size cone that contains a certain amount of light. And the amount of light that contains is our luminous flux right here, or phi. And dividing phi by the solid angle gives us our luminous intensity. So let's add some units to that. So there we have it. Candela is equal to lumens per steradian. Steradian, again, being a measure of the solid angle. And it is a specific solid angle, right? So it's not enough just to have the quantity omega, but we also need to know the particular direction, because the direction of that solid angle matters, because a different solid angle, in other words, the exact same cone, but oriented in a different direction, may contain a different amount of light coming from that light source, and therefore will have a different intensity. So let's take a look at some quick examples here. At top, we have our default option. In other words, each arrow is a lumen, let's say, and the solid angle is defined by the cone. So first off, we have the middle cone, and what I drew there was just additional arrows outside the cone. So most of you are correct in surmising that the intensity has not changed, because the total luminous flux within that cone hasn't changed. Just because there's additional flux outside the cone won't change the intensity we're measuring right there. On to the bottom example, what we did is we changed the direction of that cone so that it contained a different amount of luminous flux. In this example, we only have 2.5 arrows, so roughly 2.5 lumens contained in that solid angle. So most of you are correct in surmising that it is, in fact, decrease the intensity in this example. And that's simply because we have less luminous flux within that solid angle. So we haven't changed solid angle, or omega, in steradians, but we have changed phi, or the lumens, or luminous flux. And this is a great example of how we can kind of game the system here. So this flashlight is 10 million candle power, or 10 million candela. It's just a different way of saying candela. Remember that intensity is used to describe light in a particular direction. And so this is a good measure for this light source, because we can use intensity to describe directional light sources. However, here's the catch. Intensity becomes very large when we're focusing all of the luminous flux into a very small solid angle. So if we're asking the question, does this 10 million candle power light source emit a lot of light? I think it's safe to say for $35, no, this doesn't emit a whole lot of light, but it does emit a lot of light in a very small angle. So you wouldn't want to put your face in front of it, because the intensity is quite high, and therefore it'd be really hard on your eyes. But the good news is you would have to aim that pretty accurately to get hit by that narrow beam. So taking a look in a little more detail, how we measure intensity, we're going to use that enormous contraption, and we call that a goniophotometer. And what's actually happening here with this goniophotometer, now, a lot of times you use a stationary detector and you're moving the light source instead, and you can use the rotation of the mirror to get all of these different angles. And the key thing here is to measure all of the viewpoints around that light source. And we're using the mirror to feed those angles into a detector. So we get that measure of intensity at each angle around the light source in 3 dimensions, of course, because we're talking about solid angles in spherical coordinates. Again, you don't need to worry about how this is measured precisely. What you need to know is that we're measuring all of the angles around a light source to characterize the light coming from that light source in each direction. This is going to be provided to you again on a manufacturer's cut sheet. And it's going to be provided to you in the form of a candela table, which allows you to characterize the intensity of that light source in any direction of interest. Illuminance. Now we're getting back to surfaces. And so illuminance is our first measure directly of a surface, and that is specifically the density of luminous flux striking a surface or the lumens on a surface area. The symbol we're going to use for this is E because we already used I for intensity. And the units are either going to be lux or foot candle. Lux is the SI unit and foot candle is the imperial unit. Essentially, this breaks down, lux breaks down to lumens per meter squared, and foot candle breaks down to lumens per foot squared. But we have these particular names, and these particular names apply specifically to illuminance. Now, I want to point this out because this is going to come up over and over and over again throughout the semester. There is 10.76 lux per foot candle. Say it with me. 10.76 lux per foot candle. Don't forget to convert your units. This is the easiest way to get your questions wrong on the photometry homework. So let's take a look at the core equation that we use for measuring illuminance. So here we have illuminance in terms of the intensity, right? So we have the intensity of that light source in a particular direction. In this case, the direction heading towards the surface of interest. And then we have the angle to the surface and the distance to the surface. And in fact, the distance squared, because this is our inverse square law, which is a property of spherically radiating phenomena, in this case, light. But there's a lot of things that follow the inverse square law. Sound does as well. And it's why the intensity falls off with the square of distance as it disperses instead of just with distance. The cosine law, which is the version I'm showing you here, is just an extension of the inverse square law, which also accounts for viewpoint using that cos theta of the angle of incidence. Now, this is important in our geometry here to get this angle correct. So the angle of incidence is specifically the angle between the path of light as it's coming into the plane and the normal vector to the plane. So a normal vector is just a fancy way to say a line that is perpendicular to that surface across both dimensions of the surface. So there's our normal vector, and then we have our angle, then we have our vector that connects the center of the light source to the point of interest on our plane. So that's two legs of our triangle. And the angle we're interested in is the angle of incidence, theta of I, which is right here. Pay attention throughout this because the angle is important. And this is going to change your value dramatically if you're using the wrong angles. So let's take a look at the dimensions of this equation real quick, because I think dimensional analysis really gives us a lot of insight as to what these values really mean. So on the left side of the equation, here we have E, or illuminance, which is, in this case, we'll call it lux. And lux breaks down to lumens per area, or lumens per meter squared. On the right side of the equation, it's a little more complex. So we have intensity over distance. So we can consider this as candela per meter squared. So that's what we have right here is candela per meter squared. And let's break that down a little further. So we can break candela down into lumens per steradian, right? So this comes out to lumens per steradian times meter squared. But how does this get us to lumens per meter squared? Because we've got that pesky steradian value, right? We'll actually cancel the cos theta and the steradian value because both of these values are accounting for the point of view. And that's how our cosine law works to give us our equation of E equals I cos theta sub I over D squared to calculate illuminance on a surface. So let's go ahead and tackle an example. All you need for these two examples here is our cosine law equation. And here you have two different kinds of problems and the geometry associated with them. So both questions are looking at the same light source, but our geometry is going to change because in the second example, we're tilting the work plane towards us, and that's going to change the way that light falls on that surface. So real quick, we can break this down. And the first question here is pretty straightforward. Essentially, we just have 100 candela par lamp. So our intensity, I, is 100. And we have our distance of 5 meters. So because we're essentially falling along that normal vector already, cos theta is 0 and therefore is just equal to 1. So it cancels out. And so we have E equals I over D squared, or 100 over 25, which is simply 4 lux for the first problem. For the second problem, we do need to include that cos theta value in the equation. And so if we evaluate cos 30 and multiply that by our previous value of 4 lux, that'll get us to 3.5 lux for that problem. Now, measuring illuminance is a little more straightforward. And in fact, we do this in the field because it's no longer a value relevant for a particular light source. And that's because total illuminance at any one point may arrive from one direction or more typically from many directions. So if you think about the light falling on your desk right now, there's probably light sources in the room over your head, but there's probably also daylight coming in from the window. And what you do is you take an illuminance meter like the one shown over on the right side of this slide, and you're going to place that on the table face up, and it will use that cosine sensor. So that white ball at the top of it, that cosine sensor provides a 180-degree hemispherical view so that it can measure the light coming in to that point from all directions. So let's talk about surfaces then. There are 3 ways that light can interact with any surface. It can reflect, transmit, or absorb. Those are essentially the only 3 common options, though there's some fancy things that you can get into, fluorescence or phosphorescence. That's not what we're talking about with our equations of photometry. We're talking about just the basics of reflectance, transmittance, and absorptance, or rho plus tau plus alpha, which is always going to equal 1 for ordinary surfaces. Now, these values are dimensionless. They're a ratio. So essentially, it's just going to be a percentage. And so we can talk about the percent of light reflected or transmitted through a surface. And that's useful for a variety of things. However, before we get to the way we use those, let's talk about how light interacts with a particular kind of surface that's extremely relevant to architectural lighting design, and that is a Lambertian surface. Lambertian surfaces are perfectly diffuse surfaces. They're very common. Essentially, all matte surfaces, like my shirt or my hair, are Lambertian, and they evenly diffuse light. So for a flat surface, the intensity leaving the surface is going to follow the cosine law. In other words, intensity is always the highest along that normal vector again. And as we move away from the normal vector, intensity will fall off with the ratio of the cosine. In other words, our cosine law again. Now, this is only valid for Lambertian surfaces. It's only valid for Lambertian surfaces because we have specular surfaces, which include a direct reflecting component. So specular surfaces will include a directional reflection, and those surfaces do not follow the cosine law. However, for most things that we're interested in terms of basic photometry, we're only really interested in Lambertian surfaces. And that's where all of our standard equations of photometry are going to hold up. But it's important to recognize the difference between these two types of surfaces. So a specular surface is anything that also includes a directional reflection. For example, your computer screen is specular in nature because some of the light reflected off of it is directional. You know this because it's going to provide a bit of shine or glare. Any kind of surface that can form an image, say a reflection in a window, is specular by nature. Now, that doesn't mean it's entirely specular. It probably has a diffuse component as well as a specular component. However, it's important to recognize that many of these equations aren't going to work for us if that surface includes that specular component. So let's take a look at some quick examples. Here we have 4 different types of surfaces. We have a window, a chair, a whiteboard, and a diffuser surrounding a light source. And the question is, of these surfaces, which are specular and which are Lambertian? Working through these surfaces, we'll start with the window. You can see right away that's a specular surface. It's definitely specular because you can see the image in it, and that's a direct reflection of what looks to be the rooftop across the street from that window. So windows and glass in general are almost always specular surfaces, with the exception of frosted glass, which is meant to be highly diffuse. We can talk about that chair. Fabrics are almost always going to be Lambertian. So most of you got that one correct. That chair is primarily Lambertian. And then the whiteboard. So a whiteboard is in fact a specular surface, and that's because it has a bit of shine or glare to it. So from certain angles, you're going to be able to see directly reflected light, which means that a whiteboard is not a strictly Lambertian surface, and therefore the equations that I mentioned throughout this class that require Lambertian as an assumption won't apply to a whiteboard. And finally, we have the diffuser surrounding that light source. And again, this is going to be primarily a Lambertian surface. And for the same reason that I mentioned earlier, this is either frosted glass or possibly plastic. But the point is that it's evenly diffusing that light through it. And that's the goal of that device. Is to provide a more even distribution for the light source. So that is a Lambertian transmitting surface. We can talk about exitance, which is the total luminous flux leaving a surface, which makes it very similar to illuminance, which is the total luminous flux falling on a surface. The symbol for this is M, because we already used E for illuminance and because the lighting gods are cruel and uncaring. And so we make all of our symbols difficult to remember. Have units of lumens per area. Again, basically the same units as illuminance. However, I want to point out, and this is important, it's lumens per area, but it is not lux or foot candle. Lux and foot candles are names reserved specifically for illuminance and only illuminance. So when we're talking about exitance, we're going to report those values in terms of lumens per area, not in terms of lux or foot candle. So the main difference between illuminance and exitance is the interaction with the surface. So let's take a look at those equations. And here we have them. So the ratio of M over E, so exitance over illuminance, is simply the reflectance of a surface. Or if we're talking about a transmitting surface, it's the exact same process. So we can define the reflectance of a surface by calculating exitance and illuminance. And that ratio is also what gives us exitance, because rarely are we going to actually measure exitance directly. It's actually quite difficult to do so. So oftentimes we will measure the reflectance and the illuminance and get exitance as an intermediate value. Now we can also think of this in terms of the total lumens on a surface over the total lumens off of a surface over the total lumens on. So this is basically the same ratio as M over E. The only difference is we're removing area. So if we are talking about a single surface, then we can assume the area is the same, obviously. And so if we remove area, then we simply get the phi off of a surface over the phi onto a surface is our reflectance. And the same thing again for transmittance. However, there's a minor point of order here. It's the phi through. So the phi we measure underneath a surface, or the luminous flux we measure underneath the surface over the luminous flux falling onto that surface is the ratio of transmittance. Again, this is only valid for Lambertian surfaces. These equations are only valid for Lambertian surfaces. And in fact, we're only really going to talk about exitance in general when we're talking about Lambertian surfaces. Okay, so let's jump into another example here. So here we have the same par 38 lamp that we were calculating before. So it's the same intensity, the same distance from the work plane. But this time, we know the reflectance of that work surface, which is 50%. So using the equation from before, the inverse square law combined with the cosine law, we can get our illuminance, and we have our reflectance. So that's enough to calculate exitance, right? So this does evaluate to 2 lumens per meter squared. Remember, that's lumens per meter squared, not lux, even though those are the same units essentially, because we're talking about exitance. And remember, of course, as a check, M is always going to be less than E, because exitance is after light interacts with the surface. And as we remember from our vision and perception lectures, anytime you bounce light off of a surface, you will get less light off of it than you put onto it. Okay, our last important photometric quantity is luminance. When we're talking about luminance, we're talking about the luminous intensity of the projected area of a surface. We'll break that down in just a moment. But the point here is that it's a quantity of light leaving a surface in a particular direction. So very much like the relationship between intensity and flux, we again have that same relationship between exitance and luminance, in that we're no longer talking about flux per area, but we're talking about candela per area, which is the units of luminance. And finally, we get a reasonable symbol for this again, which is simply just L. And remember, luminance is the photometric quantity that you actually see. This is the light that actually enters the eye. And we perceive this as surface brightness, essentially. So let's take a look at the equations. And here we have L equals I over AP. And AP is simply the projected area of that surface. So what is the projected area? The projected area is simply the area based on our point of view. So if I take Post-it notes, for example, and I'm holding these Post-it notes totally normal to your point of view or perpendicular to your point of view, then we're going to have the full area of that Post-it note as the projected area, right? Now, as I tilt those Post-it notes, what's happening to my projected area is it's actually decreasing, right? So if I tilt this to the side, we're going to have a decreased area from your point of view, right? So this isn't about the actual area of this surface. It's actually about how big that surface is from your point of view. And so as I rotate that surface more and more, the apparent area or the projected area of the surface decreases again with the cosine. That's our cosine law coming up yet again. So we can expand this equation out. Instead of L equals I over AP, we can say luminance is equal to the intensity over the area of the surface multiplied by the cosine of thetas of V. Again, this is very important to get our thetas correct. So let's take a look at the diagram right here. So again, theta of V, kind of like the angle of incidence, the angle in this case is the angle of your viewpoint. That's what the V is representing. And again, this is going to be the angle between your point of view and the normal vector, which is perpendicular to the surface. So that's our thetas of V. We can also relate luminance to exitance, and luminance and exitance are going to be related by pi. Now, pi is actually, in this case, the solid angle, right? Because remember, the difference between intensity and flux is the directionality or a specific solid angle. When we're talking about Lambertian surfaces, they're evenly diffuse. And so we can talk about the entire point of view here of that whole surface, which is going to be a hemisphere. And so that's how we get to pi. And we'll break that down on Wednesday as exactly what that means and exactly how pi relates here. But we can use this now, just remembering that luminance is equal to m over pi for Lambertian surfaces only. And that's because Lambertian surfaces follow the cosine law in the distribution of reflected light, which is what gives us this nice circle here representing the reflected light, because we can draw the circle and all of our vectors fit inside it. So those are our two equations for luminance. And again, like I said, we'll break this down in more detail on Wednesday when we take a closer look at solid angles and how they work for lighting. Okay, so let's go ahead and do another example problem here. And so we're working the same problem we've been working throughout the entirety of class. So here's our setup for the problem. What we're given is the area of our work plane in this case. We're given the angle of our viewpoint, which is 30 degrees. And then finally, we're giving the intensity along the normal vector. So the intensity normal to the table is 5 candela. So we're going to need both of the equations to calculate the luminance along the given vector here. The first equation here is how we relate the intensity at the normal vector to the intensity at a particular angle. And then the second equation gives us the luminance if we know the correct intensity. So this does evaluate to 2.5 candelas per meter squared. So let's take a look at how this breaks down here a bit. So the first thing we can do is actually combine the equations, right? Because the I in our L equals I over AP equation is equal to the I evaluated in that cosine law equation. So if we combine them, we get this here, which is our luminance is equal to the I sub n, which is the intensity along the normal vector, times cos theta over the area of the surface, again, times cos theta. Now, here's an important question. Are these thetas the same angle? In fact, they are, right? So the angle of the viewpoint and the angle between the normal vector and the vector of interest is theta sub v, which means those cosine terms cancel out. So does this imply that luminance is viewpoint independent? You can think about this yourself. Take a basic surface, right? Not a mirror. So any kind of ordinary Lambertian surface, if you change the apparent surface area of that, the brightness doesn't really change, right? And luminance is in fact a measure of the apparent surface brightness of that object. So in that case, luminance is independent of viewpoint, but not necessarily in all cases, because luminance is viewpoint independent for Lambertian surfaces only. For specular surfaces, there are plenty of viewpoints which will have a direct reflection and therefore will be considerably brighter. So let's talk real quick about measuring luminance. We have luminance meters to do that for us. And these are, in fact, the meters that we'll be using in practicum tomorrow. Again, this is a field measured value, not something that's provided by the manufacturer, because this is about how light interacts with the actual surfaces in a real space. So you're going to measure this in the field. And unlike the Illuminance meter, where you had a cosine sensor and you just need to set that on the surface, luminance meters come with a viewfinder because you need to aim this in a particular direction to get a specific value. So it does matter the direction you point this device, because that'll change your value for luminance. So to summarize then, here is a great table. So this is also in the lecture slides. So I do recommend you go and take a look at the lecture slides, if for no other reason than to get the equations and this table. This table summarizes all of the photometric quantities we utilize throughout class today, and provides the units, the symbol, and a quick definition to remind you of what that value is for. So that does bring me to the end of this lecture. Thank you for your time and attention and your great work throughout on the example problems. On Wednesday, we're going to take a closer look at photometry and understand solid angles and how spherical coordinate systems affect the way light is transported and calculated.